It's always a number. It's not really a variable. The variable is your x coordinate, and that's always in the exponent for an exponential function. But it's some base to the x power. So it's sort of difficult to talk about a parent graph because the base number can always change. So just to keep it as simple as possible, we're going to do a parent graph as if the base is 2. Why wouldn't I do a base of 1? Actually, the base cannot equal 1. Why would that be? What's 1 to the first power? What's 1 to the second power? What's 1 to the third power? What's 1 to the negative fifth power? 1. The reason your base can't be 1 is because if it were, that would just always be 1, which is a horizontal line, y equals 1. This is not a linear type of function. You're going to see that the parent graph is not linear at all. So the base can't be 1. The base also could not be what other number for a similar reason? 0, because if it was 0 to the x power, what's 0 to the first? 0 to the second. And that would be a horizontal line. So the base cannot equal 0 either. You know what? The base also cannot be a negative number. Base has to be greater than 0. Let's think about if the base were a negative number, like negative 2. What's negative 2 to the first power? So if we plugged in a 1, negative 2 to the first power would give us negative 2. If we plugged in a 2, what would negative 2 squared give us? 4. If we plugged in a 3, what would negative 2 to the third power give us? Negative 8. So what keeps happening to our y coordinates as we plug in odd numbers versus even numbers? Right. They keep flipping back between negative and positive. And so if we were to ever graph that, it would be this kind of crazy flip-flopping back and forth thing, which can happen. So our base can also never be a negative number. It has to be greater than 0, and it can't be 1. Okay? So it can be a half. That's greater than 0. It can be a fraction. That's fine. That's greater than 0, but it can't be 1. So again, back to parent graph. For lack of a better simple base, we're just going to go with a parent graph of base 2. So if x is negative 3, and I'll do this over on the side, you have to remember your exponent rules. If I plug in an x of negative 3, 2 to the negative third power is the same as what? How do you handle negative exponents, Andrew? 1 over 2 to the third power, which is 1/8. So there's a point. Negative 3, 1/8. What about negative 2? What's 2 to the negative second power? 1/4. 2 to the negative first power? 1/2. 2 to the 0 power. This is an exponent rule. Anything to the 0 power is? No. 1. Anything to the 0 power is 1. 2 to the first is easy. 2. 2 to the second. 2 to the third. 8. So as I go up into my positive exponents, what's happening? We're doubling, 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 doubling. That's because our base is 2, and we're multiplying it by 2 an additional time. So it doubles, 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 doubles. That's what exponential growth is, right? Linear growth is increasing by 2, by 2. So plus 2, plus 2, plus 2, plus 2. That's linear growth. Times 2, times 2, times 2, that gets big really quickly and is referred to as exponential growth. think about going backwards. If I'm going backwards, what am I doing? Not down, I wouldn't say. Right, we're dividing by 2, dividing by 2, dividing by 2. So if you keep taking a positive number and keep cutting it in half, when am I going to get to 0? Never. When am I going to get to a negative number? Never. If you have a positive number and you keep dividing in half, it'll become minuscule, microscopically small, but it will never be 0. Okay? So let's graph a couple of these points. -3 and 1/8. 1/8 is barely above the x-axis. -2 and 1/4 is also barely above the x-axis, but would you believe it's double the distance away from the x-axis than the previous point was? -1 1/2 is a little bit easier to see. 0 1, 1 2, 2 4, and 3 8. So let's talk about this notation. As x approaches negative infinity, what does your function, aka your y value, approach? As I keep moving left and left and left, or if I kept going down and down and down and dividing by 2, dividing by 2, dividing by 2 to go smaller, 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 what am I approaching, Grace? I'm approaching 0 without ever actually reaching 0, correct? Which means this is an asymptote. The x-axis is an asymptote. So every parent graph has key features. Your asymptote here is y equals 0. That's the equation for the x-axis. Because our y-coordinate is approaching 0 as we get smaller and smaller, but we'll never actually reach 0. Good? Okay. Now the exponential growth piece comes from the fact that this is doubling. So it starts to increase sort of without bound. So as x is approaching infinity, as we move to the right on our graph, what's happening to our y-coordinate? What's our y-coordinate doing as we keep moving right and right and right and right and right? It's increasing, approaching what? Positive infinity. It's getting humongous. Because 4 would be with 16. 5 would be with 32. 6 would be with 64, and so on. That's exponential growth. Okay, any questions there? Exponential growth, something to think about. And I'll give you this example. Let's pretend someone offered you to be a garbage man for the month, for 1 month, 30 days, and told you they were going to pay you a penny on the first day, and that they were going to double your salary the next day, and then double your salary. So the next day you'd make 2 cents, and then the third day you'd make 4 cents. Would you take the offer? No. Unfortunately, you should have. Because if you take a penny on the first day, and you're going to double that, essentially 30 times, right? By day 30, so you're going to multiply it by 2 to the 30th power. You're going to double it and double it and double it and double it and double it 30 times. On that 30th day, just that 30th day alone, 2 to the 30th power times 0.01 would have been $10 million. That's how fast exponential growth grows. which means on the 29th day, times that penny, you would have made $5,368,709. So now, just on days 29 and 30, you've made $15 million. You're going to rethink that decision, aren't you? I would take the deal. Okay? Doesn't sound great up front, but it is. So just to give you a feel for how powerful exponential growth is that little thought. All right. So other key features. We always, when we're dealing with a parent graph, we want to talk about intercepts. We aren't going to have an x-intercept because it's an asymptote, but we do have a y-intercept. Now, this particular one with a base of 2 has a y-intercept of 1. What if we don't know the base? How do you calculate a y-intercept? How do you calculate a y-intercept? X equals 0. No matter what the base is, because of our exponent rule that anything raised to the 0 power is 1, it doesn't really matter what our base is, the y-intercept is always 1. So a critical point is the point 0, 1. Now the next critical point, if your x-coordinate is 1, take this. What if my x-coordinate is 1? What's b to the first power? Always what, Kaylee? I know you just mouthed it, but you didn't say it out loud. B. B to the first power is b. So no matter what your base is, your first critical point is 0, 1, regardless. Your second critical point is 1, comma b. In this case, 1, comma 2, because our base was 2 in this example. So those will be your two critical points. You'll have your asymptote, so you kind of connect those with a bend and approach your asymptote on one side and approach infinity on the other. That's your parent graph. Now we'll flip them, we'll stretch them, we'll compress them, and so on. Evan, is your headphone in your ear? You have music playing? Good. All right. So this is exponential parent graph. I want to look at one where the base is a fraction, so less than 1, and see what happens. So it's still a parent graph, so we should still have an asymptote here. Agreed? We should still have a critical point at 0, 1. And we should still have a critical point at 1, comma b, what's our b in this case? 1, comma 1/2. For the rest of our points, we're going to do our table of values. 1/2 to the negative third power. Did you know that when a fraction is raised to a negative, it just sort of flips the fraction? So that's really 2 over 1 to the positive third power. What's 2 to the third power? 8. 1/2 to the negative second is the same as 2 over 1 to the positive second. So the negative exponent reciprocates the fraction, and 2 squared is 4. What's 1/2 to the negative first power? 2. What's 1/2 to the 0 power? Because everything to the 0 power is 1. What's 1/2 to the first power? 1/2. What's 1/2 squared? 1/4. And what's 1/2 cubed? 1/8. So now let's look at our progression as we increase. As we move upwards, what am I doing to the number as I keep increasing? Cutting it in half. So as x gets bigger and bigger and bigger, what's happening to my y-coordinate? Smaller and smaller and smaller. When will it reach 0? Never. Okay? So if I plot some of these points, and connect, do we see the difference? Yeah. Yes, you did. Do you see the visual difference between when your base and your multiplier is a number greater than 1? When you multiply by 2, multiply by 2, multiply by 2, what's happening to your number? Is it getting bigger or smaller? Bigger. So when your base is greater than 1, your function gets bigger and bigger and bigger as you move along, and it's called growth. What happens if you multiply by a half, multiply by a half, multiply by a half? You're getting smaller. Multiplying by a half is the same as dividing by 2. Keep change flip. So if you're multiplying by a half, multiplying by a half, multiplying by a half, your number is getting smaller, 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 smaller. We call this decay. And you should be somewhat familiar with those vocab words: exponential growth, exponential decay. Decay is when your base is between 0 and 1. When you multiply by something less than 1, your number shrinks, shrinks, shrinks. And growth is when your base is greater than 1, because when you multiply by something greater than 1, you grow, grow, grow. What happens when you multiply by a base that's exactly 1? Nothing grows. It stays the same, right? Hence that horizontal line we talked about. And the reason why your base can't be 1. Because it's not growing or decaying. If you keep multiplying by 1, multiplying by 1, multiplying by 1, it remains constant. Hence my horizontal line. Okay? So parent graph asymptotes, just y equals 0. Parent graph critical points, 0, 1, and then 1 comma whatever your base is. You know what? For B, I'm just going to actually write base so you don't forget. The base of your exponent. Okay? As far as domain and range is concerned, the domain is what we can input. We can input any x coordinate, right? Both graphs go left forever and right forever. So the domain is all real numbers, negative infinity to infinity. Or you can say x is a real number using that notation. The range, however, is different, because the lowest value it will ever get to in each case is what? 0, but it doesn't actually reach 0, right? So I'm going to use a parenthesis and say 0 to, what's the highest y value no matter what the case? Infinity. So that's interval notation, 0 to infinity. Or if we wanted kind of xy notation, we would just say y has to be greater than 0. That's interval notation versus kind of set builder notation. Exercise 4. Are exponent functions one-to-one? First of all, what does one-to-one function mean? Or how do we tell if something's one-to-one, Nate? Correct. Now, it is a function. They're calling it a function, so of course it passes the vertical line test. Does it pass the horizontal line test? Tells us whether or not it's one-to-one. Does it? Yes. So because it passes that test, and it is a one-to-one function, what does that tell us about its inverse? What does that tell you about its inverse? If the original passes the horizontal line test, the inverse is going to pass the vertical line test, and therefore the inverse is a function. If you pass the vertical line test, that means you're a function. We don't have the skills yet to write the inverse, but we will by the end of this very long chapter. Okay? There's a whole nother type of function that's going to fit into this chapter because it's the inverse type of function to an exponential. We just don't know what that is yet. and we can't do it yet without those skills. Okay? So here, very quickly, we have the parent graph is the 3 to the x. We have a multiplier out in front. So how's that going to change it? What's a multiplier of 7 out in front of a function do? Nope. Plussing and minusing. Stretching. It's going to stretch it vertically by a factor of 7. So let me quickly just sketch the parent graph 3 to the x. That's going to have 0, 1. And it's going to have 1 comma b is 1 comma 3. And my asymptote is the x-axis. If I vertically stretch this by a factor of 7, where's the point 0, 1 going to stretch to? 0, 7. 1, 2, 3, 4, 5, 6, 7. And where's the point 1, 3 going to stretch to if you multiply it by 7? A vertical stretch is only going to touch the y coordinate. Take that point and stretch it by a factor of 7. Where's it going? 121. Good. What about my asymptote? If I take the x-axis and I vertically stretch it by a factor of 7, where's it going to go? Trick question. What do you think, Jordan? It's going to stay the same. It's 0 units away from the x-axis. If it's 0 units away and you multiply that by 7, it's still 0 units away. So that asymptote's still going to be in the same spot. So here is 7 times 3 to the x power. Was this growth or decay? Growth, because the base, when you raise it to the x power, the base was 3, and that's greater than 1. So this is growth, and you can see it from the graph. The y-intercept, we have it visually. It's 7, so part A is 7. But if we didn't have the graph to find the y-intercept, you just plug in 0, right? Y equals 7 times 3 to the 0 power. Order of operations says you raise 3 to the 0 power first, get 1. 7 times 1 is 7. What's your grade? Hi, okay. You want to do a lesson? You need a lesson, yeah. Sorry. Yeah, you're welcome. You too. Bye. And part C says, describe the transformation, vertical stretch by 7. Okay? Part C are critical points, 0, 1 of our parent graph. Now our parent graph is 1/3 to the x power, so that's 0, 1 and 1 comma what? 1 comma 1/3. So there's our parent graph. Is this part B, growth or decay? Is this growth or decay? Decay. You can see it shrinking, and you can see the base is less than 1. But what is the transformation? Up 4. So this point was 1/1/3. Where is 0, 1 going to go if you shift it up 4 units? 0, 5. 1/1/3 is going to go to 1, 4 1/3, correct? 1 comma 4 1/3, right? 1/3 plus 4 is 4 1/3. How about a horizontal line, the asymptote? If I shift that up 4, is it going to move? Yes. 2, y equals 4. So I have a new asymptote here. I cannot let my graph cross that line. Any questions? This next section is huge. Seems to come up every year, and you'll see the trick in it right away. When you look at A, does that appear to be growth or decay? What would you say? Why would you say decay? But so far I've told you look at the base, right? And the base is 2, which is greater than 1. So I guess I thought you would have said growth. It is decay, and I'll show you the logic as to, the real logic as to why. It is kind of wrapped up in that negative. That whole rule about B only works if it's strictly being raised to the x power. Then whatever the base is, if it's greater than 1, it's growth. If it's less than 1, it's decay. This is not strictly being raised to the x power. This is being raised to more than just that. So we're going to use a little bit of exponent rules here. And I'm going to split this up into 2 to the negative third to the x power. Because what's my power to power rule? Right? So do you see how I kind of reversed that rule? I made it power to power, which would be negative 3x, but I stripped it down so that I could have this being strictly raised to the x power. And then on my calculator, or in my head, what's 2 to the negative third power as a fraction? 1/8. That's 1 over 2 to the third. And now that my base is strictly being raised to the x power, now is my base greater than 1 or less than 1? That number is less than 1. And because it's less than 1, this is decay. Okay? On part B, again, I'm going to do this. This is my base of just the x power. So on my calculator, I'm going to type in 0.7 to the 0.75 rather, to the 0.2 power to figure out truly what my base of the x is, 0.944. Is that growth or decay now? Is this number greater than 1 or less than 1? So that's decay. The 2 doesn't matter, right? That's not the base of the exponent. This is the base of the exponent, so that's decay. Andrew?
You always just have to solve for x.
You have to get x to be the only thing in the exponent. So like on this one, I would type this into my calculator to figure out that my base is 1/2 to the negative 2/3 power. That gives me 1.6-ish. So is this one growth or decay? Growth. You can't really evaluate growth or decay until your base is being raised to the x power only. Does that make sense, Andrew? Good. The bottom part we already did. We already kind of talked about that. You already have your spiral, your homework. Have a great weekend.